A comet has just flared up near the sun, its brightness sharply increased overnight, and its tail spread wider than 5 full moons. A few days later, the sun unleashed its most powerful flare in months, sending a massive wave directly towards the point in space where the comet R2 Swan is speeding. On October 20th, Swan will approach Earth closer than ever, while another interstellar object passes in almost perfect alignment. As solar storms are about to unleash on the comet's giant tail, no one knows what will happen. Will the sky be illuminated by drama or fade into silence? The chain reaction has already begun, and what will happen when stellar fire meets a cosmic visitor? On September 12th, 2025, the Comet C 2025, now simply called Swan, orbits the Sun at a distance of only half a year light away, closer than Mars has ever approached Earth. At first, the numbers seem ordinary. A faint, slowly growing object with a brightness of about 7.5. The tail stretches only 2 degrees across the night sky, but comets are capable of surprises. Just 2 weeks after perihelion, the brightness sharply increases. On September 26th, astronomy enthusiasts in Japan and Australia observed the first signs, a sudden jump, almost to full brightness, raising the Swan to visibility for those under the dark sky. By the end of the day, international forums buzz with live observations, confirming a brightness spike to 5.5, then stabilizing around 5 from the 8th to the 28th of September. This is not just a statistical anomaly. Such eruptions indicate a core, a frozen central core that has endured impacts for centuries in the deep cosmos, now subjected to solar heat. As the comet moves away from its closest solar passage, the volatile substances hidden beneath the crust reach a critical point. Gases break through, carrying dust and ice, increasing the comas and feeding the tail. The effect is instantaneous. Brightness curves deviate from predictions, and each new observation becomes a hint of what is happening beneath the surface. Thermal stress, emissions, even a local collapse. All this is in play. Some observers notice hints of jet-like features near the core, possible evidence of cracks in the crust or the opening of new vents. The behavior of the comet deviates from the standard scenario, attracting the attention of both professionals and a global network of astronomy enthusiasts. The figures are clear now. Swan has entered a new phase, its inner mechanism exposed, and further actions are unpredictable. The question is not only how bright it will become, but also how the released energy will affect the structure of the comet and the enormous tail that is now unfurling behind it. The tail stretches more than 2.5 degrees across the sky, equal to 5 full moons lined up. For skywatchers, this scale changes everything. It is no longer just a blurry dot among the stars, but a structure that can be traced with binoculars, a line demanding attention even in suburban skies. The vastness means that more secrets of the comet become apparent. Dust particles, shifting rays of light, and a faint electric blue hue of the ion tail are formed under the influence of solar wind. The architecture of the tail narrates a real-time story. Heavier, slower dust remains near the comet's orbit, creating a broad solar fan. However, the ion tail, lighter and more mobile, can tear, sway, or even detach under suitable solar conditions. A tail resembling that of a swan now occupies a section of the sky wider than any city horizon, and even small telescopes can discern its structure, streams, bends, and sharp turns. For observers watching it night after night, the changes become evident. One single night can reveal a new bend, a dim stream, or a sudden bright glow when fresh material bursts from the core. The global community of comet enthusiasts is already actively responding. Astronomy enthusiasts around the world take photos, exchange notes, and share time-lapses showing the tail's movement over hours. Forums are filled with messages about subtle color changes, icy blue for ions, golden for dust, hinting at the complex chemistry occurring. The position of the comet, low in the southern sky during September and October, provides an advantage for observers from Australia, South Africa, and Argentina. However, even in the northern latitudes, there is an opportunity to observe as the Swan rises higher and the moon wanes. For everyone with even a modest pair of binoculars, the coming weeks present a unique opportunity to witness a live experiment in the physics of the solar system. The length of the tail signifies more than just a spectacle. She sets the tone for what happens when the sun sends its own shockwave into the same patch of space. The question is not only how long the tail will grow, but how it will react when the solar wind reaches it. September 28th at 8:43, Coordinated Universal Time. The sun erupts with a powerful class M6.4 flare, the strongest in several months. For most of September, solar activity was low, with X-ray readings from GOE satellites remaining steady, hinting at a lull in the current cycle. Then, without warning, X-ray sensors detect a sharp spike. The energy surge, measured in millions of kilowatts, illuminates the GOE 16 and GOE 18 graphs in almost real time. Solar physicists from the National Oceanic and Atmospheric Administration's Space Weather Prediction Center rush to assess an event, checking data from the Solar Dynamics Observatory and coronagraph data from the Solar and Heliospheric Observatory. This is not just another solar glitch. The M-class bursts are at a medium level on the scale, but M6.4 is enough to attract the attention of satellite operators and space weather forecasters. The source of the splash, active region 423.2, is a complex group of sunspots with twisted magnetic fields, located in the same quadrant of the sun that Swan is currently approaching. For 30 minutes, coronagraphs confirmed the launch of a coronal mass ejection. The initial speed of the ejection, estimated at 801,000 kilometers per second, places it among the fastest eruptions of the year. Alarm signals begin to arrive in the operating rooms. Satellite teams check protocols for radiation bursts, but this coronal mass ejection is not directed at Earth. Instead, attention shifts to what lies in its path. Time, just 2 days after the activity of Comet Swan, draws immediate attention. The duty officers note this event for cometologists, who begin to model the possible intersection of the coronal mass ejection with the expanding ion tail of Swan. For now, the numbers speak for themselves. A burst from class M at 0.84 minutes of coordinated universal time, a coronal mass ejection heading into space, and a comet with a tail over 2 degrees wide on its path. The sun, which had been quiet for several weeks, sent a powerful impulse to the same sector of space where Swan was performing. The intersection of these events is rare, and every device, from X-ray detectors to ground telescopes, now has a strong reason to closely monitor what is happening. At the NOAA Space Weather Prediction Center, the race began immediately after the peak of the flare. Analysts began receiving real-time data from the SOHO coronagraph and stereo A, reviewing frames in search of an expanding arc of plasma. A coronal mass ejection was launched at exactly 0.85 minutes UTC, accelerating to an initial speed of nearly 900 kilometers per second, enough to cover the average distance from Earth to the Sun in less than 2 days. Its angular width, measuring about 90 degrees, categorized it among the wider emissions of the year, but the key point was its trajectory. This time, the emission passed by Earth with a significant margin. Instead, the models showed that the main solar ejecta is directed towards the area of space occupied by Comet Swan. For the forecasting teams, the task was geometric. Solar ejecta do not move in perfect straight lines. They expand, twist, and sometimes fragment, breaking through the solar wind. To plan the path of the coronal mass ejection, scientists stitched together images from a coronagraph, aligning the leading edge with known positions of planets and spacecraft, as well as, for the first time in many years, with a comet whose tail is longer than 2 degrees. The coordinates of Swan, located slightly south of the ecliptic, just within Earth's orbit, placed it in the predicted corridor, but three-dimensional uncertainty remained. Without direct impact on Earth, data on plasma would be limited, leaving ground and orbital imaging as the best tools for tracking the encounter. Every major forecasting center noted this event for comet researchers. The question was whether the wide coronal mass would cross the tail of Swan or pass by without consequence. The best estimates placed the arrival of the coronal mass near the comet between 48 and 72 hours after launch, depending on the true trajectory and speed. Density forecasts indicated a moderate event sufficient to disrupt the visual perception of the tail, but unlikely to cause any earthly effects. The risk to Earth was minimal. For Swan, solar plasma entering the atmosphere created conditions for possible manifestations of distortions, disconnections, or abrupt changes in the comet's tail, phenomena that could develop over several hours and be visible to anyone observing the right part of the sky. The tools were ready, data streams were open. Now all eyes were focused on the corridor of comets. Magnetic fields determined the fate of each comet tail caught in the solar wind. When a coronal mass ejection, like the one that occurred on September 28th, rushes through space, it captures a tangled bundle of magnetic lines, each with its own direction. The comet's tail is formed from charged particles torn from the nucleus and pushed away by a constant flow of solar energy. These ions do not just drift. They latch onto magnetic lines, forming a sort of invisible connection that stretches millions of kilometers behind the comet. But the real drama begins when these lines cross the boundary between the comet's tail and the incoming solar wind. If the magnetic field contained in a coronal mass ejection is directed south, opposite the typical direction near a comet, conditions become favorable for what physicists call magnetic reconnection. This is the cosmic equivalent of a circuit breaker tripping. The lines of the solar wind field and the comet's tail collide, break apart, and quickly reconnect in new forms, releasing energy and freeing entire regions of plasma. This practically means that a comet's tail can break off in minutes, sending a glowing fragment into space, while a new tail begins to form almost instantly. The orientation of the magnetic field of the coronal mass ejection, especially component BZ, determines the strength of this effect. The southern BZ is the trigger that is most likely to cut off the tail, while the northern fields can pass with minimal changes. The process is quick, sometimes visible for several hours, and can leave behind dramatic distortions, sharp drops in brightness, or even a detached cloud of ions moving independently. For theorists and modelers, this is a rare opportunity to observe magnetic recombination on a scale that no laboratory can reproduce, with every twist and rupture displayed in the sky in real time. Every minute counts. A window for dramatic changes is open, and the rules are simple. Watch the tail, trust your eyes, and remain flexible in expectations. The ion tail of the Swan, over 2.5 degrees long, is fully exposed to the solar wind. If the magnetic lines of a coronal mass ejection intersect the path of a comet, the ion tail can bend or tear apart in just 90 minutes. A process that usually unfolds quietly in deep space is now occurring on a stage visible even through home telescopes. Spectral signatures can change drastically, and the lines of hydrogen and oxygen can shift up to 50 kilometers per second as the plasma reacts to the impact. The morphology of a comet can change in intervals shorter than the duration of a film. A bright thread may suddenly break, or a new tail may form after an event of disconnection. This is science in action, and the best data can come from amateur astronomers, anyone with a camera and a clear sky. However, caution is extremely important. Not every fluctuation or sudden dimming is evidence of a solar storm. The geometry of coronal mass ejections remains an open question, and predictions of direct collisions are still mere hypotheses, unconfirmed by facts. Experts urge caution rather than certainty. The correct approach is documentation, comparison, and reporting, creating a global database while the story of the comet unfolds. For now, the only guarantee is change. The next anomaly may appear in a single frame, and the whole world watches together. On October 21, 2025, the numbers tell a story. Comet Swan will pass just 0.225 million astronomical units from Earth, about 39 million kilometers, which is 100 times the distance to the moon. For the comet, this is equivalent to a close flyby of a planet. This is not a random approach. The geometry almost perfectly aligns. Swan's orbit intersects the ecliptic at a slight angle, following the same invisible plane that defines the main transport artery of the solar system. The position of the comet, just south of the ecliptic, places it in an area where the solar wind and heliospheric current are most active. On the same day, the interstellar visitor 3 and Atlas reaches its upper conjunction, positioned directly opposite the Sun from Earth's perspective, while Swan passes its closest point. Both objects, separated by millions of kilometers but situated in the same wide corridor, provide a rare opportunity to compare the dynamics of native and interstellar bodies side by side. For orbital analysts, this alignment is a statistical anomaly. The probability that two such bodies, one from a deep solar orbit and the other from interstellar space, approach each other near the ecliptic within a few days is extremely low. Time is also astonishing. On October 21st, the new moon arrives, eliminating the light of the moon and creating the darkest skies of the month. When Swan reaches its nearest point, the parallax effect, small changes in the visible position observed from different points on Earth, becomes measurable even with modest rear telescopes. Observations show how the Swan rises higher each night, its tail stretching across the southern constellations. The distance between Earth and the comet, displayed in real time, compresses to a quarter of the distance from the Sun to Earth, offering the best conditions for observation before Swan disappears back into deep space. For those hoping to see the Swan in the coming nights, timing and preparation are crucial. October 21st is the key date, the closest approach, new moon, and the darkest skies of the month. But the observation window is wider. The path of the Swan passes just south of the ecliptic, rising higher each night through the southern constellations. From Buenos Aires to Perth, the comet rises early and lingers in the sky until dawn, its tail stretching to the west along the horizon. In the northern latitudes, visibility improves as October approaches. After midnight, the Swan rises above the tree line and ascends higher each evening. Star maps show that the Swan is near the boundary of the constellations Pegasus and Pisces, easily found by drawing a line from Fomalhaut, the brightest star in the area. The orientation of its tail allows for comparison with neighboring stars. The length of the tail is 2.5 degrees, allowing its extent to be measured by the distance between Fomalhaut and the nearest stars. For binocular users, the standard field of view of 7 by 50 captures the entire tail in one glance. Small telescopes reveal more details, but even a camera on a tripod can capture this trail with just a few seconds of exposure. The parallax effect starts to manifest as the Swan approaches. At a distance of 0.25 astronomical units, its visible position shifts slightly depending on your location, and this can be measured with patience and careful observation. Astronomy enthusiasts coordinate their efforts across different continents, recording the times of rise and set, and exchanging data to track changes in the tail. The checklist is simple: record the position of the comet, sketch or photograph its tail, and watch for its bends, sudden bright flares, or eclipses. Each observer, whether against city lights or in a dark rural area, adds a pixel to the global picture.